Welcome back to the deep dive. So for today's deep dive, we're doing something a little unusual.
Yeah,
We're going to do a complete teardown of just a single product spec sheet,
right.
the Kramer C-SC-SC-OM4-328 fiber optic cable.
It sounds a lot like we're just reading an old receipt, but this spec sheet is actually a perfect time capsule.
A time capsule. How so?
Well, because this specific cable, even though it's discontinued, it holds the key to understanding the standards that really defined an entire era of high-speed digital video.
Okay, let's unpack that. So our goal isn't just to list the features, but to figure out what all this alphabet, OM4SC 40 GBPs, what it all actually means when you're moving huge amounts of data.
Exactly. We're decoding connectivity at, like, a molecular level.
So where do we start? The name itself.
Let's start with the core identity. It says right there, OM4 multimode fiber optic cable.
And multimode is important because
Because it means the light signal is actually traveling along multiple paths inside the fiber core. It's really effective for shorter distances, but it's crucial for supporting high bandwidth.
Okay, so in that multimode family, why is OM4 specifically so significant?
Because it represents a massive, massive leap forward. OM4 is laser-optimized multimode fiber.
Laser optimized.
Yeah. It was engineered specifically to let the industry hit 40 gigabits per second. And it did that using these inexpensive lasers that operate at an 850 nanometer wavelength. It basically gave multimode fiber one last major extension on its life.
Before everything started moving towards single mode for the really high speeds.
Exactly.
So 40 GBPs is the performance metric. But how did they actually get that data to flow through the glass? That brings us to the geometry, right? The 51125 part.
Right. That's the physical specification. It means the core of the fiber is 50 micrometers. And the cladding, which is the outer layer that reflects the light back into the core, that's 125 micrometers.
And that 50-micron core is why it's multimode.
That's it. It's large enough to accept light from those cheaper lasers we mentioned, but it's tuned so precisely to keep those multiple paths of light from getting scrambled. You want them all to arrive at the receiver without too much dispersion.
Because dispersion is what slows the signal down.
That's what slows it down.
Okay, so this spec was really optimized for places like data centers or high-end AV racks. Now let's talk about the physical connection points, the handshake.
Well, the name itself, C-SC-SC, it reveals a whole story on termination.
SC connectors on both sides.
SC on both sides. The SC connector is kind of the sturdy, square peg champion of fiber. It's no frills, all function, just really reliable and simple to click into place.
And the sources tell us the exact length. This one was 328 feet or 100 meters with the 3mm PVC jacket. But the really key thing here is where this cable was actually used.
Right. This wasn't some generic patch cable you'd find anywhere.
No.
This was the digital backbone for Kramer's own high-performance transmitter and receiver systems, the 670TR, the 670TR, the 671, the 673 series.
So that 40 GBP's OM4 capability wasn't just a number on a page.
Not at all. It was the practical solution for sending high-resolution digital video over pretty long distances. You needed that 40 gig pipe to handle all that uncompressed video data.
And it was also TAA compliant, I saw.
Oh, yeah, TA compliant. So it met all the strict government trade agreements for acquisition.
So let's put this all together for you. We've decoded the technical shorthand. OM4 tells us the speed class was 40 GBPs. 50125 defines the physical geometry you need for that speed.
Right.
And SC tells us the rugged connection method. So this cable, even though you can't buy it anymore, it really stands as a monument to that moment when 40 GBPs became a practical reality.
It absolutely does. And it raises a really important question for today.
What's that?
Well, if this laser-optimized OM4 standard was the peak solution for getting to 40 GBPs, what does it take to go beyond that? Think about what technical specs like, say, OM5 or maybe single-mode fiber, what becomes absolutely necessary when your requirements move past 100 GBPs, which is common today.
A great question. How much has the engineering had to change just to push light a little faster or a little farther?